Okay, it's 3:01. Looks like we have lots of folks logged on, so I'm going to go ahead and get started. Hi, folks. My name is Jamie Kostelnik, and thank you for tuning into the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program and mostly organized by Matt Thomas with contributions from myself and Stephen Slaughter. For those of you who are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone and video camera. We will wait until the end of the presentation to take questions. In the meantime, please do the best to make sure your microphone is muted and your camera is turned off when you are not intending to speak. So it's a real pleasure to introduce today's speakers. Matt Thomas has been a research hydrologist with the USGS Landslide Hazards Program since 2017. He studies how hill slope hydrologic processes contribute to landsliding in burned and unburned areas. Matt's research aims to improve the predictive capabilities of landslide warning criteria across regional gradients in climate geology and burn history. In his free time, in addition to organizing this seminar, Matt enjoys being a dad, fishing alpine lakes, and being a landslide nerd. Nina Oakley is a geohazards climatologist with the California Geological Survey's Burned Watershed Geohazards Program, where she has been for the past year. Prior to that, she was a research scientist in academia. Nina's scientific background is in applied meteorology and climatology. She studies extreme rainfall of the past, present, and future from sub-hourly to annual timescale. Nina also enjoys surfing, running, mountain biking, snowboarding, and watching the weather. So I think Matt's going to kick it off. So Matt, whenever you're ready, go for it.
Thanks, Jamie. I think my screen should be shared, so I'll just go ahead and get started. Thanks for that introduction, and thank you again for everybody who's tuning in today. The title of Nina and I's presentation is Rainfall Intensification Amplifies Exposure of the American Southwest to Conditions that Trigger Post-Fire Debris Flows. The title slide photograph is by Jeff Coe in our office, and it illustrates debris flow activity in the vicinity of San Ysidro Creek in Montecito, California, following the January 2018 debris flows and rainstorm over the 2017 Thomas Fire. I think one of the strengths of the study that you're going to learn about today is that it really brought together a pretty diverse mix of federal, state, and academic partners. Our co-authors are listed here, and they include folks from the USGS, the California Geological Survey, and Northern Illinois University, or NIU. The NIU team in particular brings a deep bench of atmospheric and climate science expertise. And as Nina's going to explain in a little bit, this NIU group has really developed the first climate model output that's relevant to considering how rainfall capable of triggering post-fire debris flows could evolve in the future. I'd also just like to mention that these climate projections are big data, and the computational resources that it takes to work to conduct the simulations and then work with them from a post-fire debris flow perspective is quite large. And so we're thankful we had those computational resources available to us. Before I hand it over to Nina here, for those of you that are a little less familiar, I just kind of want to contextualize debris flows in general for you. Put quite simply, these are mixtures of water, mud, rocks, vegetation, and other dangerous debris that can move downhill quite rapidly. And as you're going to see in this video that I'm about to play, these tend to be more dangerous than flash floods because the debris amplifies the depth, discharge, and shear stress that's imparted by the flow. So I've got a video rolling right now in a few seconds. Just keep an eye on the left-hand side of the screen. You're going to see an example of a debris flow that came off of the Thomas Fire 5 years to the day of the 2018 Montecito debris flows. And this is a much smaller debris flow than what occurred in 2018, but I think it illustrates all the types of things we worry about with these hazards. You've got large boulders, mud, woody debris. You might have also picked up on a propane tank that was rafted or moving with the flow. And it really just highlights how quickly conditions on the ground can change with respect to rainfall that's conducive to this hazard. And so with that, I'm going to turn it over to Nina for a little while. She's going to talk about the triggering conditions for post-fire debris flows and the state of the science on climate-driven changes to rainfall intensity.
Thanks, Matt. So post-fire debris flows are initiated by short-duration, high-intensity rainfall, and this typically occurs associated with convection and The simplest way to describe convection is vigorous upward motions in the atmosphere. And so individual areas of convective high intensity rainfall are typically small, only covering a few to maybe tens of kilometers in horizontal extent. And some examples are shown here. The red areas in these radar images indicate very high intensity rainfall, yellow more moderate, and green lighter. And these areas of convection occur within a broader, large scale or synoptic meteorological context. So for example, you can have these embedded within a winter storm, such as the example in the bottom right. We've got high intensity rainfall in these scallop shaped features along a cold front that's moving across Southern California. And these winter storms may or may not feature a moisture plume that meets the criteria to be called an atmospheric river. And the presence, absence, or strength of an atmospheric river does not indicate a storm's potential to produce high-intensity rainfall. So decaying tropical systems are another situation we see when they move into the southwest that are often associated with thunderstorms and high intensity rainfall. Of course, the North American monsoon can produce that high intensity rainfall in thunderstorms in the warm season. And there are other scenarios that can result in thunderstorms as well, as in the case you see on the lower left. Next slide, please. And it's very likely that post-fire debris flow activity will increase in a warming climate. There's consensus that wildfire activity has been and will continue to increase, but we're not going to focus on fire changes here. Rather, we're going to focus on precipitation. Some previous work by Jason Keene and Dennis Staley shows that post-fire debris flow likelihood may be more sensitive to changes in rainfall intensification, more so than soil burn severity or fire frequency changes. And we'll talk a little bit more about that study in a moment. So to inform long-term hazard planning, we investigate how the frequency, magnitude, seasonality of rainfall capable of producing post-fire debris flows will change in a warming climate. So let's take a little bit more into rainfall intensification background there. So if we take a general global view of how rainfall is projected to change relative to historic, based on different amounts of global average temperature change, we see some areas around the world where precipitation increases with temperature, especially in the high latitudes, the tropical Pacific, and some of the world's monsoon regions, not really for the North American monsoon, and some places where it decreases in the mid-latitudes. Water vapor is not distributed evenly across the Earth, and atmospheric circulations, storm dynamics will affect which areas see increases and which areas see decreases. So let's talk some more about why these changes are projected to occur. Next. So as the temperature increases, the atmosphere is able to contain more water vapor. This relationship between temperature and water vapor in the atmosphere is described by the Clausius-Clapeyron relation. And by this relation, we expect an increase of approximately 6 to 7% of water vapor increase per degree Celsius of warming. However, the actual precipitation intensification that we observe differs from this increase in water vapor depending on several factors. So let's look at, so we have our water vapor increasing at this rate of about 6 to 7% per degree Celsius. And let's look at what happens with precipitation. Next slide, please. So this is summarizing a huge body of precipitation intensification literature into one slide here, but generally we see that precipitation intensification is going to vary with the duration you're looking at, the spatial extent, and with the event magnitude. Are you looking at light to moderate rainfall or extreme rainfall, for example? So global mean precipitation intensification over long durations occurs at approximately 1 to 3% per degree Celsius. And this global mean precipitation increase is really constrained by the Earth's energy budget to increase at a rate lower than suggested by the Clausius-Clapeyron relation between temperature increase and water vapor increase. And then when we start looking at extremes and what I'm referring to by extremes here in climatology generally and in much of the literature on extreme precipitation intensification, extremes are referring to the 99th percentile of a distribution at whatever time scale of interest, whether you're looking at daily, hourly, etc. So if we talk about daily extremes averaged over a large area, say continental scale, where we have rainfall likely to be occurring with the atmosphere at full saturation, and we're likely precipitating out most of the water vapor in that, if not all of the water vapor in that column, now we see precipitation intensifying at a rate closer to that what's expected by that Clausius-Clapeyron relation. When we move down to the subdaily timescales and start looking at that 99th percentile and what tend to be these very localized areas of convection no longer at that continental scale, we start to see rainfall intensification at or above the scaling expected by that Clausius-Clapeyron relation, with some studies reporting intensification at double what is expected following that relation, so up to 14% per degree Celsius. We also find that extremes generally increase at the expense of light to moderate precipitation across time scales. And it's also really important to note that, that with this intensification at the short durations, even if an area like we saw a couple slides ago where we have some places getting wetter and some places projected to get drier, even if an area is expected to get drier on average or experience little change in long-term average precipitation, it can still experience intensifying rainfall at these short durations, resulting in increased flash flooding and debris flow hazards in a warming climate. Next slide, please. So subdaily rainfall intensification, so which for our purposes, talking about post-fire debris flows, we're looking at the hourly, the sub-hourly, and we'll really focus in on 15-minute in this talk. Why is it intensifying more than at these, say, daily timescales? So in these convective storms producing this short duration, high intensity rainfall, there's several factors that contribute to greater and more effective production of high intensity rainfall. In this warming climate, one thing is increasing moisture availability. More water vapor creates the potential for more rainfall to occur. We also have more latent heat released with more water vapor condensing, and this allows for storms with stronger storms with more vigorous updrafts and that can produce greater rainfall intensity. There's also potential for a larger storm footprint, so greater area experiencing high intensity rainfall. And as a really simplified graphic I'm showing here, in the same paper reference, there's a more detailed one that gets into the cloud dynamics and digs into each of the processes going on. There are some factors working against rainfall intensification: reduce moisture in some areas and increase atmospheric stability that will resist the upward motions are two factors. Next slide, please. So talking about these percent changes in rainfall intensification or scaling factors, previous study that helped us inspire the one we are presenting on used a scaling rate of 7% per degree Celsius and 2.5 degree Celsius change, which would be an 18% intensification in rainfall intensity applied to 15-minute duration triggering thresholds over Southern California. And they considered 3 times the triggering threshold to represent a major debris flow event. So for the considering historic period, they found a major post-fire debris flow event was likely to occur in Southern California about every 10 to 13 years. But applying this rainfall intensification factor, that increased to a major debris flow somewhere in the Southern California domain about every 5 years. And as mentioned before, an important result of this work that we apply in our study, their sensitivity analysis they did found that the changes in likelihood of debris flow activity in Southern California is more sensitive to the rainfall intensification than changes in the fire frequency or burn severity. Next slide, please. So scaling factors can help you get an estimate of future precipitation intensification, but there are some limiting factors. As you can see in the figure here, scaling factors vary with region, temperature, season, moisture availability. Scaling factors based on historic observations of precipitation intensification will not account for changes in atmospheric circulation or changing convective dynamics of storms in a warming climate. But one thing that can be done to support using scaling factors, informed scaling factors, is and address some other questions about precipitation changes like threshold exceedance, as we'll look at in this study, is using a high-resolution climate model output, which we will look at now. Next slide. So global climate models are run at a very coarse scale. So 100-kilometer grids are considered state-of-the-art. And they represent the Earth in 3 dimensions: land, ocean surface, and atmosphere. Modeling the atmosphere requires many levels. And these GCM outputs aren't really useful for studies related to post-fire debris flows, where convection is what's driving the high-intensity rainfall. And we're considering a process that's happening at watersheds that are generally at the less than 10 square kilometer spatial scale. But we can use these low-resolution climate models as boundary conditions and physical principles to input into a high-resolution regional climate model. And these are much more computationally intensive models that are run over a smaller area that can provide the high spatial and temporal resolution information needed. And until recently, and by that I mean 2023, we did not, to our knowledge, have climate model output available at the high spatial resolutions, less than 4 kilometers, and 15-minute output relevant to that would be relevant to post-fire debris flows for the continental U.S. So let's take a look at the regional climate model information we use for this study. So the regional climate model approach developed by the Northern Illinois University Group uses bias-corrected GCM input. Bias corrections performed before doing the regional downscaling to reduce bias and error. If you're interested in bias correction, there's more details in the paper reference here. They use the weather research and forecasting model, advanced research. And this is a convection-permitting model. So convection is not parameterized as it is with GCMs at a 3.75 kilometer resolution. And this is a very common model used in the atmospheric sciences to downscale global climate model output, as well as to model weather events. So very commonly used model. They call the simulation WRF-BCC for the WRF bias-corrected CESM, and the historic baseline simulation represents the 1990 to 2005 period, and then they have a future portion which represents 2085 to 2100. So 15-year historic and 15-year future period, and they run simulations for both the RCP 4.5 lower end emission scenario and the RCP 8.5 higher end emission scenario. And a 15-year period seems short, but this simulation that we're using here took about a year to run with a typical research allocation on a supercomputer. They also ran a mid-century, which is coming soon, that took about a year as well. And all these simulations together required 25 million core hours and 500 terabytes of storage. So to store the output. So hopefully that helps you understand why it's challenging to do this for a much longer period. Next slide. And so you might ask, how does the model output perform? We're interested in how these model outputs represent the statistics of the historic climate period. This is not a reanalysis product that's meant to exactly reproduce individual storm characteristics. There are a few examples in their paper. What I'm showing here, they use the PRISM 4-kilometer precipitation estimates, often considered best for representing precipitation in the mountainous west, and they find a good relationship between the model output and PRISM for average annual and monthly precipitation. There is a bit of wet bias in many mountainous areas of the west, and this may be due to a lack of precipitation observations at high elevations that could influence PRISM. And one big challenge is that the gridded precipitation estimates used to validate model output are imperfect in themselves. So in that panel D, the hatched area in panel D is showing where there's disagreement between PRISM and other gridded precipitation estimates. And there's more disagreement between PRISM and those estimates than between PRISM and the WRF BCC historic simulation. They also tested it for representing extreme daily rainfall events, where it performed well. That study's forthcoming. And unfortunately for the hourly and sub-hourly, there's not a great validation set, especially in the West, which is generally recognized as a major limitation for high-resolution models. Next slide, please. So are there limitations for regional climate models? Absolutely. Ideally, you would be running multiple models or multiple ensemble members and could evaluate how much they agree and how much uncertainty there is. But clearly, these are computationally expensive. Regional climate models are also still parameterizing some important processes, such as cloud microphysics. So they're better at representing the real world than GCMs, but are still imperfect solutions. And even at that high 3 to 4 kilometer resolution, it may be coarse to represent some convective processes. Some work suggests that 200 meters may be needed to resolve some convective processes like entrainment. But nevertheless, the regional climate model output gives us a useful tool to examine potential changes in rainfall intensities relevant to debris flows. We should use it judiciously. This is definitely not the final answer, and we should keep evaluating new data sets as they become available. So with that, Matt will show us how we used the Northern Illinois University regional climate model output to examine for potential changes in post-fire debris flow hazard.
Hey, Nina, thanks so much. And we'll be coming back to her as we break down some of the results from this study. But I'm going to start laying out some of the methodology. And as I do that, I just want to reiterate that objective statement that Nina highlighted earlier, which is that we recognize that long-term hazard planning requires projections of how the frequency, seasonality, and magnitude of rainfall capable of triggering post-fire debris flows could evolve under a changing climate. In this study, we tried to provide that information within the context of what we call rainfall threshold exceedance metrics. And so for those of you that are a little less familiar, I have an example of a rainfall threshold that's relevant to post-fire debris flows illustrated on the left. It's plotted in rainfall intensity versus duration space. Our theoretical threshold is that dashed black line. When we have rainfall thresholds that plot below that line, we would say debris flows are unlikely. As you meet or exceed that threshold, they become more likely. And when you're well above threshold, bigger debris flows become likely. And so for this study, we really tried to design the simplest rainfall threshold exceedance metrics that we could to get at the original question related to frequency, seasonality, and magnitude. And what I've illustrated with the text on the right is essentially what we're doing. We ask these climate simulations for the historical versus late 21st century scenarios. How often do we get above this line? What time of year do we get above this line? And how far above the line do we get? So that's the general premise of how we're trying to use these climate simulations for this study. And I believe this is probably the most detailed slide we have. I just want to step through, hopefully relatively briefly, about how we actually integrated or sourced our thresholds for this study. This is a 4-panel figure in the upper right left-hand corner for part A. I'm just illustrating that we used essentially 2 different rainfall threshold types for this study. The first of which is related to wildfire perimeters. So there's about 175 burn areas across the Western United States, in the American Southwest, where the USGS had conducted an emergency assessment of post-fire debris flow hazards over just about the last decade. And so for each one of those burn areas through the Southwest, there is a rainfall threshold that's issued, and that rainfall threshold is essentially a product of how steep, how burned, and how erodible that particular burn area was. And so we have this catalog of rainfall thresholds that we've issued in the past in areas where post-fire debris flows have been a concern. So that's one type of threshold. I'll refer to those as USGS-based thresholds. The second kind of threshold was essentially built off of work from Staley et al. 2020 that showed that the 1-year recurrence interval for 15-minute rainfall intensities was capable of triggering post-fire debris flows throughout the American Southwest. And so for California and Colorado specifically, we looked at mountainous terrain through both of those states and asked the question for spatially variable thresholds based on the 1-year I-15, kind of where that threshold exceedance was occurring. You might have picked up that I essentially was describing two different types of thresholds. The USGS-based thresholds are rainfall-based thresholds. These statewide mountainous terrain thresholds are recurrence interval-based. To put both of those in the kind of same space and to keep them consistent throughout our analyses, we borrowed again some work from Staley et al. 2020, developing log linear fits to Atlas 14 precipitation frequency information to convert our USGS rainfall thresholds to rainfall recurrence interval thresholds. That way, both of our threshold types are on the same page. And then we can move to part C of this figure, which is that for every grid cell in the climate model domain for the historical period, we conducted a rainfall intensity duration frequency analysis, where essentially we can build out what amounts to a function that you see in part C, which allows us to take a given rainfall recurrence interval and calculate what the equivalent WRF BCC historical period 15-minute rainfall intensity would be. With those WRF BCC rainfall thresholds in hand, we simply step through the late 21st century climate scenarios, those 15-year time series for RCP 4.5 and 8.5, and keep track of those metrics I discussed earlier, namely how often do we go above threshold, what time of year is it, and how far above threshold are we? This map on the right-hand side is showing you what the annual frequency of threshold exceedance could look like across the American Southwest for burn areas that the USGS had conducted hazard assessments over the last decade. And so those are summarized at a state level here. And each bar is representing the dark gray is the historical period, and the orange and red are the two different RCP scenarios for the late 21st century. Across the board, you can see at a state level, we're seeing increases across the board. When we put these results together, we find that the increases in the exceedance under RCP 4.5 and 8.5 are statistically significant. And so what the first finding coming out of the study is telling us is that the frequency of rainfall threshold exceedance is projected to increase in areas where post-fire debris flows have been a concern for us in the past. Looking at these statewide mountainous terrain rainfall thresholds, this is an example from California. You're looking at RCP 4.5 on the left, RCP 8.5 on the right. I think really the most important thing to take away from this plot of kind of rainfall threshold exceedances per year under these climate scenarios is that the intensification problem is not projected to be a spatially uniform one. For example, in the southeastern corner of the state, the rainfall intensification is not really as apparent. It picks up in the peninsular ranges, transverse ranges, and southern coast ranges of Southern California, but really becomes most apparent in the northern Sierra Nevada, North Coast ranges, and Klamath Mountain areas. Okay, so at first blush, that result I just showed you for California is suggesting that we could see higher rates of rainfall intensification in Northern California. I just want to add that we have a kind of growing body of evidence on the ground of post-fire debris flow occurrence in some of these places. Like, for example, Central California is shown here. This is an example of a post-fire debris flow on the 2020 Dolan fire. Scott McCoy and his student now at CGS, Dave Cavagnaro, shown here for scale. And we also have examples from Northern California and the northern Sierra Nevada. This is an example of a post-fire debris flow that was part of the largest single wildfire in California history so far. And I just present both of these field examples to highlight that we're now documenting post-fire debris flows in places where they hadn't been systematically documented in the past. Nina, I'll let you talk here.
So we see this greater number of threshold exceedances in Northern California rather than Southern California, and this does agree with other work. I'll show a bit here, and we'll show some more in a moment. But on the left, one study shows that the likelihood of very extreme hourly rainfall in the winter season increases more in Northern California than Southern California. And on the right, this study focused on 1 to 7 day periods and shows that in Northern California, that the locations they show in Northern California in the top row generally have a greater intensification of precipitation, shown by the gray line representing the historic period. You see it shift to the right to become the orange line representing the future periods. So one thing to point out, we did not dive in and evaluate the meteorological phenomena of each event, but we're putting it in the context of existing literature. Next.
Thanks, Nina. I also mentioned that we did these kind of statewide mountainous terrain analyses for Colorado, and those RCP 4.5 versus 8.5 scenarios are shown here. Again, what we learned from Colorado is that these are not spatially uniform rates of intensification. For the case of Colorado, the biggest pickup in 15-minute rainfall intensities shows up in the southwestern corner of the state in the San Juan Mountains. But looking at the context of California and Colorado together with respect to this frequency, projected frequency of rainfall threshold exceedance, what we may expect based on these simulations is more opportunities for sufficiently intense rainfall to initiate post-fire debris flows before processes like soil hydraulic recovery or vegetation regrowth can reduce susceptibility to flash floods or runoff-generated debris flows. We also have, under the present climate, many examples in California and Colorado of multiple post-fire debris flows emanating from the same area in the same rainy season. And one way to interpret the results here is that rainfall intensification could result in more post-fire debris flows for settings that are not sediment supply limited.
So some of these changes we see in Colorado as well as California could be associated with changes in tropical storm or North American monsoon activity. Speaking to the monsoon, there's a lot of disagreement in the literature on what will happen with the North American monsoon, whether precipitation will increase or decrease. Overall, the Intergovernmental Panel on Climate Change suggests there's low confidence in a decrease in monsoon precipitation, but intensification of rainfall during the monsoon has been observed and is likely to continue in the future. There is high confidence that the monsoon will start a little later in the summer season and extend later into the autumn season, and this is reflected in some of our seasonal results. And there's been limited work done on the influence of decaying tropical systems moving into the southwest in a warming climate, but projections for tropical cyclone activity in the North Pacific suggest that there will be an increase in tropical cyclone intensity, and they are projected to have tracks that extend further poleward, so further north in the northern hemisphere. And this could potentially be a cause for increases seen in autumn threshold exceedances, but we need to do more work to look into the drivers of each exceedance. Next.
Okay, thanks, Nina. I just want to dive now just into the last kind of two parts of our results or findings for this study. The first of which relates to the magnitude of rainfall threshold exceedances. In the upper right-hand panel, you're seeing plots of what we call the mean exceedance ratio. So that's essentially how far above threshold a particular exceedance was. And you're seeing those trends for mountainous terrain throughout California, Colorado, and for those 175 burn areas throughout the American Southwest. And like the annual frequency, we also find statistically significant increases in the mean exceedance ratio in these places. The implication of this kind of result is that we know debris flow volume or debris flow magnitude does scale with rainfall intensity, such that these results would suggest that bigger debris flows are possible going into the future. The last piece with respect to our results is that seasonality piece. And what I've plotted here in the middle and lower panel are the mean proportion of threshold exceedances broken out by month for mountainous terrain across California and Colorado. What I think is really neat and hopefully intuitive to most people is that on the average, California and Colorado have essentially inverted seasons for high intensity rainfall that's conducive to post-fire debris flow generation. So California is dominated by cool season exceedances. Colorado tends to be dominated by warm season exceedances. And generally, this trend going into the future based on these climate simulations seems to be consistent, although there is an slight increase in the number of exceedances that are happening in the cool season for both California and Colorado. And I think Nina's going to talk to that.
Yeah, so focusing on that intensification and more exceedances in California happening during the winter season. This is typically happening. We have extratropical frontal systems, often featuring atmospheric rivers, dominating production of precipitation. And so what we're seeing this intensification in the winter season does agree with other work, such as the study presented on the left. This shows intensification of peak 1 hour precipitation rates for storms featuring atmospheric rivers in the Sierra Nevada in warming climate using regional climate model output as well. So also seeing an intensification of subdaily rainfall in that study in Northern California. And looking at figure on the right, in California, especially in the RCP 8.5 simulation, we see an increase of exceedances in that core DJF season, December, January, February, and decreases in other parts of the year. And this is consistent with research that's shown this precipitation sharpening observed in California, where across latitudes in California, there's an increase in December, January, February precipitation and decrease in the fraction of precipitation happening in the shoulder season. Next slide, please. And one other thing that may be driving the changes we see is in this study is the transition from snow to rain. So many studies, including the one referenced here, note a transition from snow to more rain in a warming climate, especially for going to happen in those mountainous areas. You know, snow you cannot put down a large amount of water at one time due to the resistance against the snowflakes. But if you have precipitation falling as rain rather than snow, this could be one driver of the large winter increases we see in the Sierra Nevada, the Klamath Mountains, places that historically have areas above snow line. They may see more winter precipitation as rain, and then increased opportunities for exceeding post-fire debris flow thresholds. And this could also be associated with some of the increase in October events we see in Colorado, as that you might start to have, that's the start to your winter season. And so in that transition season, if under warmer conditions, you could have more precipitation falling as rain rather than snow, increasing the opportunity for debris flow for debris flow threshold exceedances. Next.
Okay, so we just have two more slides here that kind of amount to our discussion and our takeaway messages. And I think we've identified a number of research opportunities coming out of this work. The first of which is we still have a lot of the map to fill in. On the right-hand side, I'm showing a figure of the Western United States, and the orange circles are areas where the USGS has conducted post-fire debris flow hazard assessments over the 2014 to 2022 range. The dark blue dots are showing that mountainous terrain area in California and Colorado that we focused on. So there's much more of the Intermountain West that could be tackled. And with respect to places like Oregon and Washington up in the Pacific Northwest, we recognize that conceptual models for the rainfall kind of intensity duration control on post-fire debris flows there may be different than the Southwest. There's some really important mapping efforts being led by folks like Kate Mickelson up in Washington, Bill Burns in Oregon, along with USGS and academic colleagues to better understand those controls. But there are opportunities with these types of climate model output to evaluate them once those kind of rainfall intensity duration conceptual models are understood. As Nita mentioned earlier, this is just kind of perhaps the first generation of climate models that's really relevant to post-fire debris flow generation. And so we hope that there's going to be opportunities down the road to consider other regional climate models, to look at individual kind of storms more from a meteorological context rather than simply marching through time series and accounting for threshold exceedances. And of course, I think looking at the rainfall intensification patterns we have and marrying them with kind of the state of the science for future fire behavior will also be beneficial. Pulling back on that quote that Nina had posted earlier about all models are wrong, some are useful. If we step back for a minute and maybe focus less on the individual, like the numerical changes in, for example, the frequency and the magnitude that we observe in these simulations, and think a little bit more about just the regional trends that this high spatial kind of resolution climate model data tell us. For example, in California, we saw rainfall intensification hotspots in Northern California. This also happens to be kind of an area where our understanding of post-fire debris flow susceptibility is relatively unconstrained and kind of newer to us than it is in Southern California, where there is decades of longstanding and really good research. And so using these types of climate model output as an option to kind of guide and direct fieldwork that would be geared towards understanding that susceptibility on a regional basis, particularly where rainfall intensification is thought to be the worst, could be helpful. And finally, I think there are also some opportunities to consider landslide hazards, both within the context of fire and outside of fire. Within the context of fire, I'm not going to outline all the aspects of the two side-by-side drainages you're seeing in the lower left-hand side of your screen, except to say that we know that fire can enhance the susceptibility of a landscape to landslides. And there's kind of a window where that susceptibility is heightened. And we saw examples of that, for example, on the 2017 Thomas fire last year. With that in mind, we also know that landslides deliver substantial amounts of sediment to channels that can then be remobilized by future post-fire debris flows following the next fire. So, of course, I think most of us are familiar with the fire flood sequence. But these climate data may also be able to shed some light on the fire flood landslide sequence, which should give us some insight with respect to kind of going into the future. Are we going to have the types of storms following fires that could enhance landsliding beyond levels we've seen and therefore load channels with more sediment? And so I think there's some context for the hazard there as well as general landscape evolution concerns. So finally, just our takeaways that we have for you today related to this study are outlined here. We find that climate projections suggest more opportunities for sufficiently intense rainfall to initiate post-fire debris flows before recovery mechanisms, either associated with damaged soils or vegetation regrowth, can take hold. We could see enhanced mobilization of sediment and other dangerous debris, which would result in greater inundation depths and runout distances on valley bottoms, floodplains, and fan surfaces. And finally, that this rainfall intensification is projected to be potentially more severe in places where local communities, emergency managers, and weather forecasters may be less accustomed to contending with post-fire debris flows. And I think I've heard Nina talk about this, and I think it's very important that it really just highlights the need for pre-fire planning and outreach with respect to that kind of being less accustomed to the hazard. That concludes our presentation. I'm just going to hover over the references here real quick. You can catch them on a recording in case, or find Nina or myself if you have more questions. And I'll park the presentation on some relevant announcements from Nina and the CGS. And thank you for your attention. And I believe Jamie is going to be managing the Q&A if we have questions.